This is the next video in the chapter on electronic structure and periodic properties. We just finished learning about how to model matter and particles such as electrons as both waves and particles. So we're going to dive a little bit deeper into electrons specifically as waves and a few more wave properties we have neglected to mention thus far. So to model electrons as waves, which we have now determined is a reasonable thing to do, as well as useful, we need a new wave property that we didn't talk about when we first discussed wave properties. So we need to add another wave property to our list. And so that property is whether the wave is considered a standing wave or a traveling wave. I feel like this is the lead up to a joke, but unfortunately I don't have one. So electrons are standing waves, spoiler, but we'll talk about traveling waves first because they're a little bit more relatable. So in a traveling wave, the energy moves with the wave. That's what W/ is for with the wave. So the wave physically moves in space and it takes the energy with it. For example, this wavy line is supposed to be water on the ocean. And in the ocean, you have waves, and those waves physically move. First, the wave is over here, then it moves, and it's over here, and then it moves over here. So it's moving physically through space. And if you were to pick a particular point on the surface of the ocean, that particular point would at one point in time be at the lowest point of the wave. It would be at an intermediate height of the wave, at the highest point of the wave, at the medium point of the wave, at a lowest point of the wave. It would, all of the different parts of the wave would at some point in time be at this physical location because the wave is moving and it's taking its energy with it. So the kind of wave we want to talk about that an electron can be modeled with is called a standing wave or a stationary wave. And that's because its energy is stationary. So the energy of an electron wave isn't physically moving through space, it is limited to one spot, and it remains there in that spot. So rather than the position being the factor that changes, in a standing wave, the factor that changes is the amplitude. The amplitude varies. Position. So we can think of several examples of a standing wave. The classic example is a jump rope with one person standing and holding it on each side and waving it up and down. Or you could think about a violin string vibrating in place. But my favorite example is to draw a microwave, which is not an electron wave, but it is still a wave. That's a standing wave. So we can draw a microwave. Let's put some time on the clock. Let's say 5 seconds. And then I'm just going to draw a line down the middle of the microwave horizontally to help me draw a wave. So a standing wave is fixed at both ends, meaning that at the center line, at the 0 point, both ends are touching. You can picture someone holding either end of a jump rope. And then the wave is stuck inside of this box because the energy is stationary and it doesn't move. So here at the ends, these are fixed ends. Also this one, just like two people holding the ends of a jump rope. And this wave moves in time. So it starts out here, these parts are in the positive region and this part is in the negative region, and they rotate up and down. They stretch from positive to negative and switch. And it's difficult to show, so I'll make an attempt at a drawing and then I will show a drawing that someone else made in the hopes that it's a little bit more clear. So I'm going to show how this moves during time by changing the time on the clock on the microwave. So we started at 5 seconds. I'm going to model it at 4 seconds and at 3 seconds and at 2 seconds to show how the wave is changing in the same physical space as time goes by. So as this wave oscillates over time, it starts out with a positive, negative, positive shape. And then later, the positive, negative, positive shape is the same, but it's a little bit smaller. And then as time goes on, it inverts to a negative, positive, negative shape. And then it becomes larger, a larger negative, positive, negative shape. And then it returns. It goes back to be a smaller negative, positive, negative. Then it inverts to positive, negative, positive, and back to a very large positive, negative, positive. And it oscillates back and forth in this position. If that doesn't really make sense what that looks like, here is another picture that might help you. So here I've drawn 4 waves on top of each other, a pink one, an orange one, a green one, and a blue one. And I guess if I wanted to be technically correct, I could draw an even bigger black one with the same amplitude as the pink one. And so all of these waves represent the same wave at different times. So as the time changes, each of these points moves from largely positive to largely negative and back to largely positive. So if it was a jump rope, the jump rope would be oscillating in time, moving from a high point to the low point, but not actually moving in the x direction in space. So there are a couple of important points about standing waves that we need to add to our list of wave properties. And the first of them is the length of the wave. You might have noticed that I drew 1.5 wavelengths here. So the wavelength is from one point all the way to the same point in the next cycle. So this would be 1 full wavelength. And so inside of the microwave, I've drawn 1.5 times the wavelength. And that is because only half wavelength sizes are permitted when you have a standing wave. So let's write that down because that's important. So the wavelength of standing waves is quantized, just like energy is. There are only certain values for the number of wavelengths that can fit inside of a standing wave. So only multiples of the wavelength over 2 are allowed in the box or in between the 2 people holding the ends of the jump rope. There have to be a multiple of a half a wavelength inside of the box. If there is a different length, then the destructive interference would take out the wave and it would eventually be destroyed. So any other wavelength value would be destroyed by destructive interference. So if I wanted to draw a wave inside of this microwave, I could draw a half a wavelength. I could draw 1 full wavelength in the box. I could draw 1.5 wavelengths like I have here. I could draw 2 wavelengths, and so on and so on. I can only pick a number of wavelengths to fit inside of the microwave that's a multiple of half of a wavelength. So that quantization is one important feature of a standing wave. The other important feature of a standing wave is that it has nodes. And nodes are points on the jump rope that are not in motion. And they're easiest to see on this other picture we have here. So if you look at the maximum point where this arrow is, as this jump rope is moving up and down, this particular point, the jump rope here, moves from a very high point to a very low point. It is moving vertically up and down, even though it's not moving horizontally. But there are a few points in this wave that aren't moving at all, horizontally or vertically. And those are points here, right on the horizontal middle line. No matter how we move from the pink to the orange to the green to the blue line, this point is always in the same spot. So that point is called a node. It's a place where the amplitude is always 0. Meaning that there's no energy from the wave at that point. In the context of a microwave, the nodes would be right here and right here for our wave. Note, the endpoints at the edge of the microwave are not nodes. The nodes have to be interior points, so let's add that. Interior points not in motion. So this 1.5 wavelength wave has 2 nodes. And in the context of a microwave, you can think of the nodes as cold spots, because these places where the amplitude is 0 are not receiving any energy from the wave. And so if you were to have a plate of food inside the microwave, these points would still be cold when you take it out. This is why your microwave spins. And this is also why your microwave dinner instructions tell you to take it out and stir it in the middle, or else there are going to be cold spots where the amplitude is 0 inside of your food. Hope you have appreciated this lesson on how to use a microwave and why microwaves were built this way. But all this to say that this wave that we drew in the microwave is an example of a standing wave. An electron is another example of a standing wave. An electron wave has quantized possible wavelengths, and it has interior nodes. So we will talk more about that in the next video about the Schrodinger model of the atom.